Welcome! We're diving deep into DeepSeek's Manifold-Constrained Hyperconnections, or mHC. This innovative technique is fundamentally changing how we think about residual connections in large language models. First, let's understand the problem. Residual connections, while essential, have become a major bottleneck as LLM architectures scale up. Since ResNet, residual connections have been critical. They ensure gradients can flow deep into the network, preventing training collapse, and this design was carried over into transformers. However, today's large language models are vast. When models scale in depth and width, that single residual stream turns into a narrow channel, restricting all information flow through one path. This brings us to the core architectural question. How can we widen this crucial residual pathway to increase information bandwidth without breaking the model's training stability? DeepSeek's answer is mHC. Before mHC, there was the hyperconnection, or HC idea. While promising in theory, it proved disastrous in practice. Hyperconnections extend the residual stream into multiple parallel channels. Instead of one path, the model has several streams that are designed to exchange information, providing higher bandwidth and better feature mixing. The problem lies in implementation. HC replaces the standard identity mapping with learnable mixing matrices. As the network gets deeper, small amplification errors in these matrices compound across layers. This structural instability causes signal norms to explode or vanish. DeepSeek reported that in a 27B model, unconstrained HC resulted in signal gains over 3,000 times, causing catastrophic divergence. It simply breaks training. DeepSeek's solution, Manifold-Constrained Hyperconnections, or mHC, addresses this instability head-on by mathematically constraining how the residual streams interact. mHC fixes instability by constraining the interaction of residual streams. Specifically, it forces the connection matrices to live on a stable mathematical space known as the Birkhoff Polytope. Concretely, this means each connection matrix is made doubly stochastic, enforced using the Sinkhorn-Knopp algorithm. Both the row sums and column sums must equal 1. These manifold constraints fundamentally solve the numerical stability issues that plagued the original hyperconnections. First, doubly stochastic matrices guarantee norm preservation. No matter how deep the model scales, residual streams will neither explode nor collapse, restoring the key stability benefit of identity residuals. Second, mHC allows controlled, balanced information exchange. Every stream contributes and receives without any single stream dominating, turning the residual path into a stable feature fusion layer. Crucially, unlike standard HC, stability in mHC does not degrade with depth, making it essential for the kind of extreme scaling required for next-generation LLMs. Wider residual streams increase memory traffic. To make mHC usable in production environments, DeepSeek invested heavily in system-level optimization. They implemented kernel fusion to minimize memory I/O, selective recomputation to save memory by recomputing activations during backpropagation, and dual-pipe overlapping of communication and computation. The result of this systems engineering is profound. A 4 times wider residual stream is achieved with only a 6.7% training time overhead. This is the difference between an academic idea and a production-ready blueprint. Empirical results confirm the theory. mHC significantly outperforms standard baselines on large-scale LLMs. Testing on a 27B parameter transformer, unconstrained HC showed severe loss spikes and unstable gradients. In contrast, mHC remained perfectly stable throughout training and consistently outperformed standard transformers across multiple benchmarks. DeepSeek mHC proves that residual topology matters, and mathematical constraints can unlock new architectures. This is not an incremental tweak. It's a robust blueprint for future stable and scalable LLM architectures.